We are currently in alpha 1.0.1_01. This version of the game added 2 new redstone components. First being the redstone dust. This can carry a on or off signal. Secondly, we have a redstone torch. This can provide an on signal to a redstone line. Additionally, if you power the block that a redstone torch is on, that will deactivate the torch and will no longer provide a signal to a redstone line. Now, despite only having these 2 components, we can do any computation that we want by combining these in certain ways. First example is an OR gate. So you have 2 inputs like this, right? And then we'll have an output here. So we call this input A, this input B. Input A is on and input B is off. Then we get an on signal. And obviously if both inputs are off, then we get an off signal. Now if input B is on, we get an on signal. And then if both inputs are on, we still get an on signal. So if either or of these inputs are on, or both of them are on, get an output. Next gate is going to be the inverter gate or the NOT gate. And then this is actually what I already showed you. It's a redstone torch like this. Then if we have an off signal here, get an on signal. If you have an on signal here, get an off signal. So it just splits state. Now, we can do something a little fancy with these 2 different components, is we can actually combine them to make a new gate. So if we have 2 NOT gates like this, right? 2 different inputs. And then we OR these together. And then inverse that OR. We get something called an AND gate. So if both inputs are off, our output is off. If A is on but B is off, output's off. A is off but B is on, our output is still off. But when both signals are on, our output here is on. So if A and B are on, and only when A and B are on, we get a signal out here. Now, we have an inverter here between the OR of these 2 NOT gates. If we remove this inverter, that'd be like if we inverted the AND because we're removing one level of invertation. So if we do that, if both of these are on, then this is off. But any other state will have the signal be on. So like this. And if both are off, it's still on. Additionally, if we go back to our OR gate, so we just have like this, and we throw an inverter on that, and this is now a NOR gate. Previously, we had a NAND gate. Now this is a NOR gate, so if either one of these signals are on, then we get an off. But if neither of them are on, then we get a on state. So these are the most basic logic gates. There is another one, but we'll get into that gate later. Now, using these gates, we can create basically any computation we want and create certain redstone devices which can take signals and do interesting things with them. One thing we can do is actually hold a state. So instead of like having a redstone torch here or no redstone torch have a signal, we can actually just hold a signal without having to like place or break a torch, which is very useful to be able to like have variables in computation, which can, and a variable is basically just something that holds a number for you. So, and you can later change, so you can like add 2 numbers, get a sum, then use that sum later on. You store the sum in a variable. And that will allow you to like build many different interesting things, like different programs, whatnot. And there's no beds in this version, so gonna have to spend for the night and go mining for more redstone, I suppose. And as we do this, I'll talk about what I want our redstone computer to do, because we will be making a computer out of these basic components. So the first thing I wanted to be able to do is hold different numbers, have both variables I was talking about. Both be stored in things called registers. Registers can be assigned numbers and have their numbers change over time throughout a sequence of instructions called a program. And we will use these registers as inputs into another component known as an ALU. That stands for Arithmetic Logic Unit. And that will be able to do calculations like adding stuff together, subtracting, and it will also be able to do bitwise operations. And bitwise operations is basically just those logic gates I showed you. It can be like and, or, but it can do it with like multiple sets of bits at once, which is actually pretty handy for different programs that you may want to use. And additionally, we're going to have something known as a CPU, Central Processing Unit. This will basically read whatever instructions that we wrote to create a program and execute them in sequential order to be able to do some sort of task like add two numbers together, calculate all the numbers in a Fibonacci sequence, stuff like that. And it's going to be basically the central thing that can control all our points. So it's going to say, like, when we write a number to a register, and which register is going to be, and when things are going to be turning on and off throughout the computer. It basically makes sure things happen when we're supposed to. And later on, as we get access to more components, we'll be able to do more things, like maybe at some point when we get redstone lamps, we will be able to make some sort of display of some kind, like a 7-segment display, be able to display numbers, which should be pretty useful if we want to make like some sort of interface, as like some sort of like maybe like calculate different different operations like a calculator would, add, subtract, that type of stuff. And also, we might want to make something called RAM, which stands for Random Access Memory. Registers are usually quicker accessing, so than RAM, because with RAM you got like a lot of different memory locations, but with registers it's one memory location, so you don't need any time to like find where the memory is, activate it, that sort of stuff. So registers are a lot better when you need to do a whole bunch of calculations in series, which is really important if you want to do something like find all the numbers in the Fibonacci sequence up to some given value, because you don't want to be like having to have that delay of RAM all the time. So having these registers which can like communicate to LU faster is important. While the RAM is kind of more important for like if you need like a whole bunch of data that you're not going to be like accessing all the time, but you need it to be stored somewhere, be accessed later. That's kind of what RAM's mostly meant for. So I think what we're going to do, now that I got some redstone together here, is going to show you how we make our first little bit of memory. And it's going to use some logic gates to do that in a certain pattern, which may look confusing at first due to like how memory works, because it's kind of self-referencing, if that sort of makes sense. Like the inputs of the logic gates kind of feed into each other, but that is needed to be able to like hold a state, because otherwise you couldn't be able to actually hold a state if it logic gates weren't self-referencing, because you would just have like these pulses that go on and off all the time, and you won't be able to like hold that, because the logic gate will just always be reading the next signal that's coming into it. So you need some sort of self-referencing to actually be able to hold a state. So I'm gonna light this area up. So this thing that I'm about to show you is called an RS latch. And I'll explain to you why it's called that in a second. So this torch is now on. Okay, so see what's happening here is that this torch here is powering this line, turns this torch off, which means this line's deactivated, which means this torch is staying on. As soon as this line deactivates, what's going to happen is this torch is going to deactivate, turning this line off, and then since this line's off, this torch is going to turn back on, and that's also going to power that line, which means we'll basically be holding a state here that is on. So we do this, and you see that's now held on. And then we can do the same thing over here, and then basically the same sequence will happen, but like with the upper line holding now holding state. So basically, when you power this line, you could consider that as setting the bit. So this could be our actual like bit of memory that we have here. So powering this, that's called setting. And powering this here, it's resetting it to 0. And that's why it's called an RS latch. And this is basically the easiest type of memory you can really have in a computer. So you see, we don't even need to have a torch here to say that it's on. We can break it, and it's staying on. Then we can just turn it off by putting a little pulse here, 1 second signal here, and just hold that state. And when we combine multiple of these together, we can hold more states, because this right here, this can be on or off. That's 2 states. And we have the second one next to it. Then this can be on and off, and the other one will also be on or off. So that's 2 times 2. That's 4 different states. If we had a third one, that's 2 times 2 times 2. It's 8. So for the amount of like signal lines we have here, also known as bits, we have a multiple of 2 states. So for the amount of signal lines that you have, you do 2 to that many bits you have, 2 to the n, and then that's going to be how many different states you have for each part of your memory. And we can use this to store different numbers. So if all signal lines are off, we could say that's 0. If the first signal line is on, but all the other ones are off, that could be 1. If the second signal line is on, but all the other ones are off, that could be 2. And that's how we're going to be able to like store numbers using these little modules here. And then later on, we can be able to add those numbers together, which is going to be sort of the first kind of computation our computer will be able to do. And after that, we can like build up some more different instructions, and then we can use those instructions together in interesting ways, create different kinds of programs. which is basically like the whole theory of computing. So Minecraft Alpha, even though it's like really infantile stage of Minecraft, it has like computer theory built straight into it, which is pretty cool. So that's gonna be the end for this video here, but we'll be making some more videos, and we're gonna build out a full computer in Minecraft.